Hi everybody, today we'll talk about Benford's law, which can be used to catch people who are cheating on tax forms. So we'll start with this graph, which is a happy graph because it shows an amount of money in an account that you hold. You put in a few $100s at time zero, and then you just sort of sit and watch, and it grows. So you don't put in anything, you don't take out anything, it's just interest giving you more money. Of course, this could also be a debt. And it bends up because usually we expect this to be an exponential function. So constant times e to the RT, where the constant is the initial amount of money and then R is your interest rate. We can do some interesting algebra with this equation. If you take logs on both sides, you get, let's do natural log of b equals, now we have a product of two things. So that's the sum of the logs, natural log of c plus natural log of e to the RT, but that is just R times t. And so natural log of b and t are linearly related. And that means that on a graph showing t versus log b, you should see a straight line for this situation. A kind of old-fashioned technology for doing this thing is semi-log graph paper, so semi means half, and that's because on the horizontal axis, you have an ordinary linear scale, where if you move a fixed distance to the right, that represents going forward 1 year in time, no matter where you start. But the other axis is not linearly scaled, it's log scaled. And what that means is that if you start at one value and move up until you double it, so from 1,500 to 3,000 is doubling. If I start from 4,000 and go to 8,000, that's also doubling. And these two arrows have the same length. Or I could go from 5,000 up to 10,000, and it would still be the same length. And so an exponential function would look linear on this kind of plot because every year, your money gets multiplied by a fixed factor. That just happens every year, so it keeps going. So that's why it looks like a straight line on this graph. Now, Benford's law comes in when you pick a random time on this graph. So if you have something that's varying linearly and you choose a random time, and then you ask about the number that comes out of that, that number is not very likely in between these 9,000 and 10,000 marks. It's much more likely that that number would be between 1,000 and 2,000. It just spends more time in this region than it does in that region. So if you pick a random time, it's likely that the thousands digit would be 1 more often than it is 9. And something similar happens for all the other digits. There's more distance here than there is there. There's more distance here than there is here. So 1 is more likely to occur in the hundreds place than a 7, and a 0 is more likely to occur in the hundreds place than a 9. And when people make up numbers because they're lying, they often don't make up numbers with the correct distribution of digits. And this is one of the basic tools that auditors can use to try to catch people. And it works even for stuff that's not growing steadily with interest. If it's going up and down randomly in the stock market or something, it's still composed of lots of small multiplications. And so it's even for that kind of random process, it's going to more likely be in these tall intervals than in the small ones. All right, so that's Benford's law.